Hi there, welcome to the fourth live session. Before we begin, this lesson is probably going to be slightly different to the ones that we've done before, in that there'll be more questions where I'll be asking you to draw a diagram. So if you remember, when I do this lesson, when I'm finished with the lesson, the PDF of the questions then go online onto the website. So it might be an idea for those questions just to watch how I draw the diagrams, and then you can practice them if you want to download that document later. Okay, now the first question isn't one of these diagram questions, and I'll just get started straight away with it. So there you go. It talks about a wave machine. I'll talk later about different types of waves and characteristics of electromagnetic waves, for instance, but this question's to do with water waves. It says a wave machine in a swimming pool produces waves as shown below. Determine the wavelength and amplitude of the water waves. So here we have the markings in the question are showing us that the distance from this point here all the way along to here, that's 3.4 meters, and the distance from here to here, in other words from the top of this part, if you remember, this is known as the crest of the wave, down here is known as the trough, so that distance is 0.3 meters. Now if we're counting these waves, then hopefully, switch on that pointer again, you should see that from this point to the next corresponding point, the next point in the wave like this would be along to here. So that means of course we've got one wave, two waves, three, then four. So it must of course be that 4 wavelengths is equal to 3.4 meters. And that obviously means for part A, the wavelength, which of course can be drawn in the equation, V equals F lambda. If you remember that equation, we can write lambda as the wavelength. Of course, if we know that 4 wavelengths is equal to 3.4 meters, then of course the wavelength will be 3.4 divided by 4, which in this case, as you know before, I'll be switching to and from the calculator. Nothing much to say about this question. Remember again, we were given 3.4 as the distance, so 2 significant figures. So we'll write our answer 0.85 meters, 2 significant figures. Now the amplitude, you can write amplitude as a capital A. Amplitude doesn't actually come up in any of the equations in the relationship sheet. I'll just write it in full. Amplitude, and I'll go back to the diagram. The amplitude is, if you imagine this dotted line, if of course this is talking about a swimming pool, if the wave machine was switched off, then of course the water would settle at this line here, the dotted line. But of course as soon as that wave machine starts, then the water molecules themselves of course start moving up and down. You imagine someone throws in a football or something like that into the pool. The football itself would be bobbing up and down as those waves, say in this case, maybe move from left to right. Okay? To measure the amplitude, it's not from the top of this crest down to the bottom of the trough, it's just from the top to the middle, or from the middle down to the bottom. So in that case, if we know from the top to the bottom 0.3 meters, then of course the amplitude is 0.3 divided by 2, which is of course 0.15 meters. Now we'll talk a little bit later about water waves and what they share in common with other types of waves like the electromagnetic spectrum, and I guess how that differs from sound waves. That's something that's coming up later. Now what we need to do is remember that number here, our wavelength, because we'll be using that in the next question. So if I can find the next part of this question, it is this one here. Right, what does it say now then? A lifeguard finds that the waves travel the full length of the 25 meter pool in a time of 5.2 seconds. Calculate the frequency of the water waves. Now of course we should hopefully be thinking of the equation V equals F lambda. When we're talking about waves, the speed of the wave can be worked out in 2 ways. In this case we actually know the distance that it's travelling in a certain time, so we can use speeds distance over time. but the other way is v equals f lambda. If we multiply the frequency in hertz by the wavelength, which is in meters, that also gives us the speed. In fact, in this question we'll use both equations. So we switch that pointer off. The first thing we'll do is we'll work out the speed of the waves from distance over time. Remember, of course, I have said in the past that really you should write the equation as it is in the relationship sheet first, just in case you make a mistake. And of course this equation is written as d is equal to v times t in the relationship sheet. So I've rearranged that one already, and it says that the distance is travelling is 25 meters in a time of 5.2 seconds. So go to the calculator and divide 25 by 5.2, 4.807. We don't want to write all those numbers. So again, we've got two significant figures in both the distance and the time. So we should have two significant figures in our answer. Gives us, of course, 4.8 meters per second. Now, if you remember, of course, the question was actually asking us not for the speed, but, and this is it here, calculate the frequency. Now, I will be losing this number, I would imagine, if I move it up slightly. So remember, that wavelength is 0.85 meters. We'll not use this amplitude. So 0.85 meters. And we also know the speed is distance over time, 4.8 meters per second. Now, as I said, the other equation we can use to work out the speed of a wave is v equals f lambda. And then, of course, if we divide both sides, it's actually the frequency we want. So if we divided both sides by lambda, we would get f is equal to v divided by lambda. So therefore, f is equal to v divided by lambda is equal to, we had 4.8 meters per second we just worked out. The wavelength, remember, we've got it all the way up there, 0.85 meters. And that gives us an answer of, go to the calculator again, 4.8 divided by 0.85, 5.64. Now again, we had, this was two significant figures, a wavelength we worked out as two significant figures, and the reason was that the data we had before that, of course, was given to two significant figures. So really our final answer for this again should be written as 2. So 5.6. But again, as I've said in the past, you are allowed two figures too many. If I was to say 5.65, in this case, that would still be fine. If, of course, I was to say 5.64, then that wouldn't be correct. So we're talking about frequency. So, of course, this is measured in hertz. And there we go. That's the first of the questions. Now, as I said, I'll be drawing a few diagrams today. And the next question involves me drawing a diagram. So if I can just show you this one. Right, there we go. Now what I'll do is I'll get rid of this piece of paper, and I think what I'm actually going to do is to draw something else before I actually answer this question, complete the diagram. When I place this in the PDF document, this diagram will be larger. If you've seen the PDF document before, the diagrams are fairly small. So what does it say? It says a man notices that when he fills his coffee mug full of water, he can see a 20p coin which was dropped into it. When the mug was empty, he couldn't see the coin. So maybe it doesn't look clear in this diagram, but this mug right here is full of water. And it then says draw a ray diagram to show how light from the coin reaches the man's eye. Now what I'm actually going to do before we do this, I'll get rid of the calculator, and it looks as if we'll need to see more of the screen, so I'll show you this. Now this represents a glass block. So let's imagine we've got air here, this is glass. Now one thing you might be asked for is maybe a definition. This is a question, by the way, if you haven't guessed this, a question about refraction. And if you're talking about refraction, if you're looking for, say, a definition of refraction, it's important that you talk about not the bending of light. Light doesn't always bend despite the fact that it's refracting. When you're talking about refraction, you're talking about the change in speed of a wave as it passes from one material to another. Now let's say, for instance, I will draw this in red. Remember, of course, we've said before in your actual exam, it will say at the front to complete the test in either black or blue ink. Okay, now this isn't the answer, of course, to our question, but let's imagine we took a ray box and we aimed our light, a ray of light, in this direction here, like so. What's obviously going to happen is that light is going to pass straight through the block and won't bend. If you remember as well, this surface here, we usually draw a line known as the normal at 90 degrees, not usually a dotted line. So we normally draw a dotted line along here, and if I'm pointing the ray box along like so in this direction, so that the actual angle of incidence would be 0 degrees here. The normal would be along here, and this would have an angle of incidence of 0 degrees. It's still refracting, because what's actually happening is that the light in air is travelling at 3 times 10 to the power of 8. So V in air is equal to 3 times 10 to the power of 8 meters per second, and when it's in the glass, the speed of light slows down. Now you'll see this in the data sheet at the start, 2 times 10 to the power of 8 meters per second. So the speed is changing, and this is actually refracting, but it's not bending. So bending of light doesn't always happen in refraction, but what does happen is this change in speed. And going from air to glass, this is what's known as a more optically dense material, the speed is decreasing. And you'll see those numbers, the values of the speed of light in different materials in the data sheets. Now let's say, for instance, I was going to aim the light at a different angle. So let's say I was going to aim it like so. And of course, if you're drawing a ray diagram, remember the arrows. Now in higher physics, there is actually a relationship between the angle in air and the angle in the material. But we don't need to know that in National 5. So there is an equation we can use. So if we were asked to draw these diagrams in higher physics, we need to draw them very accurately. We'd know what the actual angles were, not to National 5. So if we have this angle here in air, this is what's known as the incident ray, and this is the angle of incidence. Okay, in this case, the angle in air is the angle of incidence. And what we do know is as the light passes from air into glass and it slows down, this ray is actually going to be moving downwards, it's bending towards the normal. Now, we don't need, as I said, we don't need to know exactly how much, but if we had to draw this diagram, you wouldn't want to draw it along like so. That would show no refraction. It would be slowing down, but it wouldn't show any bending. And as we said, the light might not always bend. It didn't bend in this case when the light was passing straight along the normal, but it will here. So at any angle other than 0 degrees, it will actually bend. But we certainly can't say that the light always bends. That's not the case. So there you go. Remember the arrow again, so that this is the angle of incidence, and in this case, this is the angle of refraction. And as we said, the angle in glass is smaller than the angle in air because it's basically bending towards the normal. But again, light won't always bend. Now what would happen if the light was then to pass from the glass out to the air again? The exact opposite. So in this case, of course, it's striking this, what's known as the air glass boundary, at an angle other than 0 degrees. And in that case, it's actually going to bend the other way. And of course, if this surface is parallel to this surface, then this ray here will be parallel to this ray, what you could call the emergent ray, which is the ray, of course, leaving the block. I can just get that drawn like so. There we go. Now in this case, we're just thinking about the light striking this surface, between the glass and the air. In this case, of course, this would now be the incident angle, or angle of incidence, and this angle would be the angle of refraction. So in this case, the angle of refraction would actually be larger than the angle of incidence. That's when the light is passing from the glass to the air. As it was passing from air into glass, it was the other way around. Okay, sometimes in some questions you'll actually see maybe this angle marked. So if, let's say if this angle was marked as 50 degrees and you were asked to work out or to state what's the angle of incidence, note this one. This is from the surface to the angle of incidence here. The angle of incidence in this case, if we're just talking about this ray which is striking the glass boundary here, the angle of incidence of course would be 90 minus 50 would be 40 degrees. So that's just a little, something just I guess to mention before I actually draw the diagram. Now, the diagram itself looked like this. And let's see, find the ruler again. A lot of things to have to maneuver all at the same time. If this is the person's eye, then of course there is no direct path. You can't see through the cup from the eye to this coin. Remember we said as well this cup is full of water. So I guess what's going to happen in this case is I sometimes find it, I sometimes find it easier to think of the ray travelling from the person's eye as if a laser beam from the person's eye moving from air, and of course it would be refracted towards the normal downwards towards the coin. There's something known as the principle of reversibility, which means if the light was actually passing in the opposite direction, it would take the same path. And that's what is happening. So light somehow is shining on this coin and it's moving like so in this direction, and as it goes from the water in this case, which is more optically dense than air, it would then refract away from the normal towards the person's eye. So we would need to draw something that looks like so. I'll go over this in a second once I've drawn it. Remember of course that we did say to draw arrows, but the direction of these arrows is very, very important. And as I said, in order for us to see this coin, light is reflecting off of it and then moving in this direction towards the person's eye. You don't want to be showing the arrows going in this direction. So yes, the arrows should of course be in this direction as I'm showing here. And just in case you were asked to draw the angle of incidence and the angle of refraction, well, there's the surface of the cup, and at 90 degrees to that surface, I guess in this case this is the air-water boundary, we could draw this line here. Remember, this represents the normal. We always draw this normal line at 90 degrees to this surface, and we measure the angles from the normal. So in that case, this angle here would be the angle of incidence, and since it's going from water to air, the angle of refraction would be larger than that. As I said, we don't need to know exactly what these two angles are. That would be higher physics. Now, as I said as well, when you download that document, the PDF of the answers, this diagram would be larger. So as you can see, this is larger than most of the diagrams I draw. Now, let's see. What I'm going to do is I'm going to go backwards and I'll show you, I think I drew that fairly well, but just to show you, here we are here. Yeah, that's basically what we're looking for. That just gives me time, I guess, to find the next thing I'm going to be looking for. Now, this isn't a question, a mini lesson, I guess, on wave characteristics, and hopefully there's an awful lot of diagrams that I've drawn, and I'm hoping before the final exam to put these on YouTube if there's time. Now, and this is one of the slides which I've shown, and basically it shows the two different types of waves, longitudinal waves and transverse waves. And the questions I've put up so far, the first question was about water waves, and of course we said about water waves, you can see that water waves are basically transverse waves. I was talking about, let's say this was again waves in that swimming pool. If the wave itself was moving from left to right, and we were to place, say, a football on top of that water, the football itself would just be bobbing up and down. That's represented by this blue arrow. So the particles themselves making up that wave, say water particles in that case, are just moving up and down, but the wave itself is moving, in this case, from left to right. So as I've said at the top, transverse waves. That's where the particles vibrate at 90 degrees to the direction of the wave, as you can see. So this is the particles vibrating up and down. From left to right, that's the direction of the wave. Anything which moves, I guess, in that nature is a transverse wave. And it's important to remember that all electromagnetic waves and water waves as well, as we said, are all transverse waves. Now we'll talk about the electromagnetic spectrum, but all electromagnetic waves are transverse waves, as are water waves. A second type of wave is this type here. And as I've said, sound waves. That's the type of longitudinal wave that we need to know about. In this, if you imagine, let's say just here is an air particle, then as the wave is moving from left to right, the air particle itself is moving from left to right as well. So the actual particles, the air particles in that case, they vibrate parallel to the direction of the wave. And this here, I guess this would be where the air particles are squeezing together, known as a compression. Over here, a position where the air particles are spreading out, known as a rarefaction. But as I said, the air particles moving left to right, parallel to the direction of the wave as the wave moves from left to right. So just remember that sound waves are longitudinal, water waves and all the electromagnetic waves, they're all transverse. That obviously is something which could come up. Now I am going to ask a quick question, which is another numerical one, which is why I'm going back to the lined paper. Oops, if I can find where the lined paper goes, just there. Right, let's see. Just find the question. And we're looking for this one here. Okay, now this question, talking about electromagnetic waves, this is talking about a weather satellite. I'll move this ruler out of the way. A weather satellite orbits the Earth at a height of 36,000 kilometers above its surface. Calculate the time taken for a radio signal sent from the satellite to reach Earth. Now, the important thing is, again, we spoke about a speed of waves before. The electromagnetic waves, as you'll see, something I'll talk about in a second, they all travel at 3 times 10 to the power of 8, the speed of light. So you will see at the start of the data sheet the speed of light, and it's not just visible light which travels at that speed, it's all of the electromagnetic waves travel at that speed in air or in a vacuum. So in this question, V is equal to 3 times 10 to the power of 8 meters per second. And we're being asked to find the time it takes for those waves to travel 36,000 kilometers. So as I said before, the equation we would use, it looks like this in the relationship sheet. Distance is speed over time, or that can obviously be rearranged to speed. So distance is speed times time, or speed is distance over time. We can rearrange that one to give us time as distance over speed. And remember that that distance of 36,000 kilometers should be converted to meters. So multiplied by 10 to the power of 6 times 3. And then, as we said, the speed 3 times 10 to the power of 8. And bringing the calculator again. Now, I've said before again, in these questions, of course, you really need to know the position of this button here, times 10 to the power of x, or in some calculators, exp. I'll not say too much about that just now. So 36000 times 10 to the power of 3 divided by 3 times 10 to the power of 8 gives me 0.12 seconds. Now I don't obviously need to round that because I've got two significant figures. And there we go. Now Another mention of electromagnetic waves again. What I'm going to do is I'm going to show you a diagram again, which looks like this. Right, this basically shows the electromagnetic spectrum. What it doesn't show though, and I'll show that in a second, is the order, or at least all of the members, I should say, all of the members of the electromagnetic spectrum. It is showing on the left hand side radio waves, on the right hand side gamma rays, but if you were asked to fill in the blanks, to fill in the names of all of the electromagnetic waves, would you be able to do it? That's something that's very important to know. Now, before we look at that, so maybe it's something you could be thinking about. If you're asked what they all share in common, well, of course, they all transfer energy. I've not said that on this page, but all electromagnetic waves transfer energy. All waves transfer energy. The last question, we did actually rely on this fact to answer it, that all of these waves in air travel at the speed of light, 3 times 10 to the power of 8 meters per second. We also said, of course, we're talking about the difference between longitudinal waves, that was sound, and all of the waves in the electromagnetic spectrum, they're all transverse. Another difference between sound and the electromagnetic spectrum, or the waves in the electromagnetic spectrum, is that unlike sound, all of the electromagnetic waves can pass through a vacuum. And the other thing is as well, if they have in common a common speed of 3 times 10 to the power of 8, then as the frequency increases, the wavelength decreases. So remember, the equation we're talking about, of course, is speed is equal to v is equal to f lambda, and this velocity is going to be constant. So I guess what that means is, as that frequency increases, in order to keep this velocity constant, what would then have to happen is that the wavelength would decrease. Okay? Now, the left hand side of this electromagnetic spectrum, this is the long wavelength end. So as I said, there could be a question where you have to fill in the blanks, where not every single member of the electromagnetic spectrum would be written in. But the left hand side, at least as I've drawn it, it could be drawn, of course, from gamma on the left to radio waves on the right hand side. But radio waves anyway, they have the longer wavelength. Because they've got the greatest wavelength, they have the lower frequency. This thing here about lower energy, we learn in higher physics a principle known as wave-particle duality. So we talk about the electromagnetic spectrum as being a family of waves, but we also talk about light, and of course not just visible light, but any of these waves in the electromagnetic spectrum also having properties, I guess, of, say, like particles. So we talk about light particles known as photons, and the energy of these photons is related to the frequency. So over at this end, the gamma rays, they have the greatest frequency, and basically the energy of these photons is directly proportional to the frequency. So over in this end here, the right hand side, gamma rays have the greatest frequency and therefore have the greatest, gamma ray photons have the greatest energy. Okay, so it's important to know radio waves at one end have the longer wavelength and therefore the lower frequency and lower energy. At the other end, the gamma rays have the shortest wavelength, greatest frequency and the greatest energy. Now, as I said, if you were shown a diagram of the electromagnetic spectrum, but some of these names were not filled in, I'm trying to find the next diagram, here it is, would you be able to identify all of the members? And here we have it here. So, I guess what we need is some method of remembering the electromagnetic spectrum. Now, I did look online, and one that I managed to find is reading music is very unsatisfactory for xylophones, which of course xylophone starts with an X, and glockenspiels. Might want to write that down, it's up to you. So reading music is very unsatisfactory for xylophones and glockenspiels. Quite a few years ago, when I worked in a school in Aberdeen, some of the pupils thought up a rhyme in that school, I guess what you could call a mnemonic, a way of remembering something. And the one that they came up with was related to someone who played James Bond from 1971, Live and Let Die, all the way up to 1985 in the movie A View to a Kill, and that's Roger Moore, who played James Bond 7 times. And they came up with Roger Moore invents very useful Xbox games. Now, it doesn't matter how you remember this, as long as you have some method of remembering the order of the electromagnetic spectrum. Now, we showed in the last diagram, you need to know which end has the largest wavelength, which end has the shortest wavelength, and also know that the longest wavelength has the lower frequency, and so on. But also need to know, obviously, the correct order. And as I said, maybe you should be showing a diagram slightly like this, but of course there may be two of the waves missing, and you would need to identify them. So there you go. Roger Moore invents very useful Xbox games. Or as we also said, reading music is very unsatisfactory for xylophones and glockenspiels. Now we've got 5 minutes left, and I know I've got 2 diagrams to look at, so I'm going to move on. And what I'm looking for is back to another question, is this one here, which is talking about diffraction. Now, we spoke about refraction before. This is diffraction. Refraction, remember, was talking about the change in speed as light, or any wave, I guess, passes from one material to another. Diffraction, that's the bending of a wave around an object. If I was to get rid of this, I do actually have 2 diagrams which I can show you. I'll get rid of the calculator, get rid of the paper, and I shall show you this in a minute, which is just a larger version of this diagram. Again, this will be in the PDF document. Now, before we go to full screen, the question says radio waves are diffracted as they pass over a hill. Complete the diagrams below to show the effect on long wave and short wave radio signals. So the important thing to remember is that the longer the wavelength, the more diffraction we see. So I'm actually going to start, and I'll go to this page here with, if you can see that there on camera, shortwave radio. I'll start with that, and then I'll show the difference with long wave. Now, when I draw this diagram, move that calculator right out of the frame, it's important how I actually draw them, I guess, as I show the effect of having no diffraction to start with. And when you're drawing these diagrams, it's very important that when I'm filling in this side here, that the wavelength, it's not going to change. Unlike in refraction, it's not something I've mentioned, but I can mention that in the PDF. Now, it looks as if from this wave to this wave here is roughly 1.5 centimeters. Of course, in the exam, I would imagine that would be drawn more accurately. This is just something I drew quickly in the computer. That means that, say, from one line to the next would be 0.75 centimeters. I'm going to just quickly mark the tops of these waves like so, and then in the middle. Obviously, you would want to take a little bit more time, so of course I'm doing that at the top of these waves, and also at the point, the same height as where they're striking the hill. And as I said, I'm going to draw this as if there was no bending of these waves at all, to start with at least. There we go, one more. And if I then fill these in, 1, 2, 3, 4, 5, 6. There we have it. So of course that's showing no bending at all. And as we said, this is shortwave radio, so compared to long wave radio there would be less bending. Now, what I would then do, now you can draw a little dotted line along this, along here, but I won't draw that. What I will do though, is I'm going to draw a dotted line just to show some diffraction around this hill. And as I said, you would actually get more diffraction if the wavelength was longer. So there we go. So I'm going to say that these shortwave radio signals are going to diffract round like so. Now, of course, if there was, say, a house here with an antenna on top that was trying to pick up the radio signals, probably be no signal at all. As the wavelength increases, more bending, more diffraction around this hill, and the reception would be better. What I now want to do at this point is, remember I drew along to the bottom of these lines here. I now want to just curve them round until they strike that dotted line, like so, to show the bending of the waves around the hill. So there we go. Now I'll compare that to what I've got in the long wave in a second, but I'm just going to follow exactly the same method. Now with these lines, again you can see it's about 1.5 centimeters between these waves. So I'll just draw the first three. And the same at this point here, where they strike the hill. 1, 2, 3. So as I said, step one is really just to draw this with no diffraction, no bending. And where before we maybe drew the dotted line to about here to show the bending of the waves around the hill, with a longer wavelength there's going to be more bending. So I'm going to draw again a dotted line, but at a greater angle. So of course they're bending round more. And again, from the bottom of these lines, curve them round until they hit that dotted line. As I said before, the most important thing in these diagrams is to make sure that when you're filling in this side here, that the wavelength from here to here is the same as it was in the part of the diagram that was drawn for you. And if we now compare the two diagrams, this is the first one, the short wave radio, this is the second one, the long wave, and of course you can see that the larger the wavelength, the more diffraction we're getting, the more these radio waves are bending round the hill. There we go. Now again, we need to know that. We need to know that the larger wavelength would bend round more, but there's no relationship we need to know in National 5 in order to work out what this angle would be. If we were asked obviously to draw this diagram, and this, let's say this was what we were shown, and then we had to fill in this diagram here to show the effect of a larger wavelength, obviously it would need to be noticeably different. So this angle here needs to be noticeably larger than this angle there. Right, now I'm just wondering if there's time to show the last thing. I'll show it anyway, and if I want to say any more about it, I'll just write that in the PDF document. So something else you might need to draw, at least a different type of diagram you might need to draw, would be if we get diffraction. Sorry, I'll just close this. There we go. A diffraction at a gap. And what have I written here? I've said the amount of diffraction depends on. So before, remember we said with our obstacle in the way of that wave, as the wavelength increases, the amount of diffraction increases. Now it's the same with this, but so in fact I've written that in the second or the last line. I've said as the wavelength increases, the amount of diffraction increases. So let's imagine that we were drawing this diagram, we had to draw it again, say for maybe a smaller wavelength. So if we had a smaller wavelength, then we get less diffraction. Now all I've done here is these lines, as they strike this gap, I've just drawn, first of all, a line from here down to here as if there was no diffraction, and then from here down to there again, and then from here down to there as if there was no diffraction. Okay, the next thing I've done, as before, when we just had the one obstacle, the hill, I've drawn a dotted line like so down here, and then continued the line from here, curved it around until it hits that dotted line. If the wavelength was shorter, then this dotted line here, which shows the bending around the obstacle, I would draw that at a smaller angle, say along here, because of course there'd be less diffracting, less bending around that obstacle. Second thing is that as the gap gets smaller, the amount of diffraction increases. So it could be again that this is another diagram that you would need to be able to complete. In the live lessons, what we've done before is we've concentrated, I guess, on the relationships. We've worked out lots and lots of different mathematical, or used lots of different equations, been using the calculator in most of the questions. But what I would like to say at this point is, of course, spend some time just looking at the diagrams in this unit. Look in the past papers and see the kind of questions which could come up. It's a type of question which is often overlooked when someone is studying. So just make sure that you would know how to fill in these questions on diffraction and refraction. And I guess that is about us for time. So again, thank you very much for watching. The questions that I've put up today and any other notes that I might want to include will be on the website eventually. Hopefully, if not by the end of today, then tomorrow. So look out for that PDF document. And thank you very much again.